Let's go through the basic concepts of maximum likelihood estimation.
So far, we have talked about random variables and their probability distribution. In fact, the probability distribution of data is often unknown and likely complex. In machine learning, we try to model data distribution using a parametric function, p sub theta. But the parameter of the function theta should be learned from data to make the observed data samples as likely as possible under the model distribution. The algorithm for doing so is generally known as the maximum likelihood estimation. After learning, we may consider p sub theta as a generative model that approximates the data distribution.
For example, here shows the samples of a 2D continuous variable. Looking at this scatter plot, we may speculate that an elliptical-shaped probability density function can well fit the data distribution. We may define a parametric family of functions that all look elliptical in shape. Different choices of the parameter theta give rise to different elliptical shapes. We can use likelihood to measure how well a model fits the data. For example, a parameter setting in blue gives you a model distribution that does not fit the data at all. Another model shown in green is better but still mismatched with data. The model shown in red is clearly the best and has the maximum likelihood. When the likelihood is a smooth function of the parameter, we may search for the optimal parameter using an algorithm rather than doing trial and error. The model may start with a random parameter and progressively refine the parameter until reaching the maximum likelihood.
Let's define likelihood mathematically. Our goal is to make the model distribution p sub theta close to the unknown data distribution p sub theta. In other words, the model should put a high probability exactly where the data tend to occur. Mathematically, we can measure the overlap between the model and the data distribution by integrating the model density p sub theta weighted by the data density p sub theta over all possible values of x. This expression can be written as an expectation, so we can think of the likelihood as the average model density p sub theta when x is drawn from true data distribution. We want to tune and search the parameter theta to maximize the likelihood, which is the expectation of the model density p sub theta for x drawn from the true data distribution. We should note that the p sub theta is between 0 and 1, and usually in a very small range close to 0. It's often more convenient to use log likelihood instead of likelihood. Taking the log turns a number close to 0 to a much larger negative number. The log function is also monotonic. The parameter theta that maximizes log likelihood also maximizes likelihood. Maximizing the log likelihood is equivalent to minimizing the negative log likelihood, which defines the loss function for machine learning to model the data distribution. In practice, we draw independent data samples from the unknown data distribution and evaluate the average negative log likelihood across the sample as the loss function. The maximum likelihood estimation, or MLE, of the model parameter theta is the minimizer of this loss function.